So in the background, what we will see is something like this. Okay, we have a high-level point of view, and we assume that this computer executing my code is having at least a CPU with multiple core or multiple CPU. Okay, now they're different. Okay, you can go to your department server list. Okay, there is some computer with more than one CPU. Okay, but put it simple, every core can execute one process. So you have a multiple core, you can have multiple processes running in parallel. So this is the scenario that, let's say, we have a CPU have multiple cores. So after you execute this fork system call, now keep in your mind that the kernel is not something living. Okay, kernel is a piece of code. You are executing system call so that you are being the process, but executing the kernel code. So you won't find this guy executing in parallel with the orange guy, right? So you're jumping to the kernel level, execute kernel codes, and by the time the kernel say that, okay, duplication finish, start to run again, and this guy will run in parallel, these two guys. Now, in the background, what is going on is very simple and boring, okay? So the boring process like this, first of all, believe it or not, in the kernel there is a double linked list, okay? Yeah, we call it text list. If you're interested, you can take a look at I don't know, maybe you have to ask your friend who has taken my elite class last semester. We really try to take a look at the double linked list inside the kernel, try to process it, pick a particular process and destroy it, okay? So this is double linked list, not sorted in any order, okay? But you will find this identifier. The identifier is a PID, okay? So as let's say my target of executing the fork system call is 154. Okay. Now, what is going on? You will always have an illusion that, oh, when I do a fork, okay, the next PID is 1235. Okay. So actually, this 1235 is I just hard coded, right? But it may not be always 1235 because you may have a distributed, not distributed, I say multiple processor there. And the multiple processor, they all call fork, okay? Now, then who get 1235? So it's not a guarantee. The guarantee is only these two guys are different. And usually, the new guy has a higher PID, okay? So remember, this is not a must by adding one, okay? So, oh, sorry, I skipped this, okay? So, but by the duplication, which means that this process structure inside the kernel contains a lot of things. So one of the things we have here, like, let's say the running time, okay, is a number, an array of open files. Later on, I will show you a program in playing with this array of open files. And the PID of them, they all duplicated. And after duplication, we will update the new guy, okay? The new guy is this guy. And what is the mean of update? Let's say the running time, because you just created, so your running time should be 0. And I've already told you that the array of open files is preserved. Later on, you will see this how this array is preserved. There are some pointers, but you don't have to care about this. Just a relationship, okay? I am a child, this guy, so I have a pointer pointing to my parent, so that I know that you know when I want to know who is my parent, I can follow this pointer to find it out. And here is a list of children. Maybe this is an array of pointer. Maybe it's a linked list. This is a care, just a list of child. Why you need this list? Because if you remember what we have taught last Tuesday about the weight, okay, weight system call. The weight system call knows that whether I have any children. If I have children, then I have to wait if you call weights. Okay, I have to wait if you call weights. That means that I'm suspended. Okay, I'm suspended when you call weights. So this list is very important, so that we know whether we have to wait or not. Now, what is going on next? Next is very interesting. Is about the user space memory. I told you that the user space memory will also be duplicated. What is the meaning of duplication? It means that all these guys, okay, the code, the malloc, local memory. Now, local memory is very important. When you duplicate local memory, local variable memory, okay? Local variable memory, it means something. Let's say, before you call fork, you call function A call, and function A call function B call function C. Okay, let's say something like this. And inside function C, there is a fork system call. Now, function A, B, C are all functions, and they have local variables, and they are all hiding in this area. Okay? Maybe you understand the concept, but if you don't understand, don't worry. In chapter 4, we'll go to revisit this. Okay? Every functions when you call will create local variables, and what I mean is really duplicating this area. It means that even this calling order, you have called A and called B and called C, all the local variables are preserved. So that when you come back means that the CPU finished the system call and go back to either one of the process, they know that they are inside the function C, not function A, not the main. Okay, it's function A and then call function B and function C for both guys because they are preserved for the local variables. Malloc, of course, last time we showed this, I call malloc, okay, and then I call fork. The malloc memory is being duplicated. Global and constant both are duplicated. It's very easy to understand, just duplication. And the last is before you end this system call, you set the two return value inside the kernel. Okay, the kernel control what is the return value we should get. Let's say this is the parent guy. Okay, I highlight this. Okay, so this is the parent guy. The parent guy will know that to make the name of my son. So I know it's 1, 2, 3, 5, but the children you usually don't know the parent's name, so it's a 0. Now, this is about the fork system call, and I want to tell you about the importance of why we have a duplicated array of open files. Okay, I don't know whether you know this 3 guys. Oh, this 3 guy, not this 3 guy. This 1, 2, 3. Okay, how many of you don't know these 3 guys? Standard in, standard out, standard error. Okay, last lecture during the break, there's one student asked me, "Hey, what is this?" Okay, how many of you don't know these 3? Raise up your hand. Anyone? Which one do you don't know?
None of them.
You know none of them. Okay, very good. Okay, don't worry, yeah. Make sure that you know what it is. I write a test program, test.c, okay? So you, how many of you don't know this call? Okay, raise up your hand. printf. How many of you don't know this? Good, everybody. Only you know. Then do you know how to print things to a file? Yeah, then this is fprintf. Okay, good. Okay, so printf and fprintf, you know what it is, right? Printf, I will say hello world. Okay, so this print to the screen. Now, this standard out guy, okay, is a file stream, okay, is of type, is of type of this file. It means it is a file stream which is open for you, okay. And when you do the following, what will be the results? Okay. So the results will be identical. So what is meaning of identical? Actually, the printf and the fprintf. Printf is a I would say is a shorthand. Okay, it's a shorthand. It's a alias shortcuts to this fprintf standard out. Okay, it's shortcuts. And let's do another thing. This is the thing that last time people asked. Okay, then what is this guy? Okay, to make a difference. Okay, so what is this guy? Let me get the results out. Hey, did I compile it? Oh no. Oh, I'm afraid. Yeah, you smile. That means that you know the answer, right? So you can see this 2 guys stand out very clear. It's an alias. It is a shortcut of printf with fprintf as well. But how about standard error? Standard error is a stream, okay, for printing error. But it seems to be nothing different from the standard output. Okay. This is only a year 1 level of view. Okay. Now you are non year one, okay? So I will, some of you are yes, okay, but I don't care. Yeah. So let me show you something different. So do you know what this will go? What does command actually do?
It writes to the text file.
Yes, we will write the output to text file. But take a look here. The ono is not really ono, okay? That's why I choose ono. It won't go into the file. Okay? So what is the meaning? The meaning is something related to this guy as well as the standard output. The standard output is for outputs. Okay? And some people design this symbol to redirect output only, but not error. Okay? So the error stream will still comes up in the screen. And you can see it like this, okay? So the error stream is usually to report error. And this is up to you whether you choose to implement that way, okay? Now, these two guys I explained. This guy and this guy. Now how about this guy? This guy is very hard to explain because you seldom write program like this, okay? Now, first of all, let me ask. How many of you don't know this? F scan F. Yes, scan from a file, right? Yeah, scan a number from a file, okay? But this time the number is called stand in, okay? Okay, so then I have this program. Test.c. Okay, compile it, run. Okay, so it's waiting for me. Now you know it's waiting for me because we are actually reading from standard input. Okay, I said that you never write in this way because you seldom scan things from file. Okay, but if you have tried this, you understand that now this means that actually scanf is a shortcut, right? Shortcut of fscanf standard int. Now let's say f10 is over 10, So these three guys are streams, okay? In C++, that means a C in, C out, okay? Now, these three guys, when you do a fork, okay, fork system call, actually you will inherit them from your parent. So what does it mean of inherit them from your parent? You know, your parent process is actually using the terminal. It is terminal for getting input and putting outputs. Now, what is the meaning of duplication? The duplication is your child. Why this feedback is so strong today? Okay, let me do something first. Okay, better. So what is the meaning of duplication now? The duplication means that you will actually inherit the terminal as well. Well, should I stand here? No, stand here is better. So you duplicate the terminal. You output the things to the same place as your parent. You're reading things from the same place from your parent. Okay? So that means that after the fork, you won't say that, where is my standard in, where is my standard output? You don't have to worry because you inherit. Okay? You inherit from your parent that your parent using the terminal, and after the fork, you will also use the same terminal. That's why the importance of duplicating this array of open files is very essential, necessary, and sufficient for you to survive in writing programs. Okay, if it's not duplicated, I don't know what will happen. Okay, so this is point number one. But there are always pros and cons, right? This is a good point. How about the bad side? The bad side is, let's take a look at this diagram. This diagram, I already written a program. Okay, you can find it in the GitHub. And what is this program is about? We have two processes. Original is one, but I call fork. Okay, I call fork. But before you do the fork, what we have done, let's take a look at the program. It's called share the open file. Okay, I hope that you can understand. Now, when you take a look at a certain kind of program, okay, you have to make sure that you understand which part will be executed by the child, which part is executed by a parent. Okay, and tell me, what do you think about this program? I shouldn't say what do you think, okay? But how many lines will be produced inside that file called data.txt. I give you 1 minute, okay? Talk with your neighbor and discuss. Okay? How many lines will you produce on that file? Okay? You can have two cases. Let's say you cover your eye, there is no fog being called, okay? Then I think you know what this program is doing. Okay? Should be fine, huh? Using F3 and FR. Okay? So let's say if you cover the fog, okay? Then how many lines will you produce? 10, right? But what if we have the fog? Ah, interesting, huh? Let's run the program first, okay? I put a sleep here. I put it there on purpose. I don't want one of the process dies and then another process to execute. I want them to execute in parallel. Okay, so that you run for some time, I run for some time, and eventually you will stop. I do it on purpose. Okay, so let's go. So it will wait for some time because by random, okay, sometimes it will wait for 1 second, sometimes it don't wait, okay. And you know, %2 means either return 1 or 0. Okay, good. So let's take a look how many lines we have inside the data.txt. How many lines? Yeah, it's written there. Okay, 20. 20. Why we have 20? Huh? Take a look at the program again. It seems to be stupid. Before the fog, you open a file, okay? And what is the permission? Rights, right? That means that I will create that file if it doesn't exist. If it exists, I will truncate it to 0 bytes and start writing from the head. And both files knows that, not both files, both processes. Both process knows that we have inherit or not inherit, we have opened this file. Okay, one guy is the one who opened, one guy is the one who inherit. Okay, now two guys know that I have opened that file and I can write to the file without any problem. Okay, of course there will be chances that you want to write fprintf and fprintf generate error, but as long as you find the content of the file is something like this. Take a look. What is that? Maybe you have missed the printf here. The printf is I will print the PID and then the loop counter. The loop counter will start from 0 and then 1, 2, 3, 4, 5 up to 9. Okay, and take a look at the data here. The first process, okay, execute once, print a sentence 0. The loop counter, then the second process 1 again, okay? But you know why they have a 0 here and both are 0? Because the I is duplicated. When you duplicate the I variable, they go to 2 different processes and they have isolated memory. When you change the I, you won't change my I, okay? But this is the facts. Fog won't duplicate the hard disk. Okay, you will say that I don't have fog if you don't want more hard disk here. then I don't have to buy any computer. Okay, yeah, keep on doing fog. Now there's only one hard disk, so always that file, no matter how many fogs you call. So that 2 sentences will go to the same file. Okay, 2 sentences go to this file, this sentence, and it is clear that the parent, that is the older, the smaller PID guy, have sleep for some time so that this guy have a chance to print things. Okay, and the stories continue. So happen that I have a beautiful pattern, 0, 0, and then 1, 2, and then 1, 2. I don't know why they're so beautiful. Okay, and then all the way down until you get both 0. Okay, now this is very interesting. How interesting it is? The interesting point is when you print a thing there inside that file. Okay, although 2 guys want to print, and they actually won't overwrite each other. I print one line, you print one line, and I will find a line that interleaving two pieces of data. Okay? So that means that the hard disk control or the file system control inside the kernel already support the feature that you allow two processes to open the same file at the same time. There is a control, and then which is allowed so that both process print things, it will match. I mean, not a mess, even an overwriting. Okay, so this is the very interesting control, and the interesting control doesn't end there. Take a look at my program. I am a good programmer. When I open a file, I will close. Okay, and the interesting point is also about that close. The close is, do you know what is the meaning of closing file? Maybe you don't know, right? Every lecturer before this class will tell you that, hey, you open a file, please remember to close it. Okay? For me, I don't care. Okay? Why? It's because it depends on the context. What is the context? Context means the place that you're executing. The place you're executing here is a special context that a file being opened twice. Because you duplicate something, okay? And the parent or the child, when it calls close, it won't really close the file, right? If, let's say, a parent closes the file first, then the child try to write more piece of data and then close, he will fail. But you won't find it here. That's if there is a counter inside the file that, oh, I know that there are two guys opening it. I expect to close, so that I will finally close this, okay? And how many of you have written Objective-C program? How many? Oh, I'm surprised. Okay, so if you're writing Objective-C program, you also heard of this feature. We call it reference counter. Okay, there is a counter in Objective-C program that monitor memory, disk memory, and count how many people are pointing to it. And in the kernel, there is also the same thing. There is a reference counter to see how many people are pointing to this file. We have two, and we expect the two guys will call fclose. If there is only one guy calling a fclose, I will close the file. I will wait for the both guys. Okay, so this is something really interesting. And what is not interesting is when it comes to your assignment. Let's say your assignment, you open a file accidentally, and then you keep on doing fork, and then you find out why I cannot close the file. Okay, because there are some processes open a file, but you forget to close it. Okay, so this is the nightmare, as well as something inheriting good files. Let's say this is a good file inheriting, but the nightmare is you open but forget to close. Okay, so this is about share opening files, and it's just because of the fork system call design. And how about execute? Execute is very easy. Let me see. Oh, I still have time. Execute is very easy. So how easy is this? Oh, sorry, this diagram is useful. This diagram already has shown before. It means that you are a process, okay? You are the people. I give you a script, and you follow the script to execute something. And I changed from this script to another script. So you restart everything, but you are still that guy, okay? This is how I describe execute system call. Now, how about in the kernel? In the kernel, it's very easy. In terms of a CPU execution, the CPU look at the code that we are executing. First, I understand there is a guy executing the blue code, and I don't care as long as you are the orange process. Okay, I don't care whether you're executing blue code or green code, but certainly you say that go to the kernel do something for you, and from the CPU point of view, I don't care which code you're executing. You just give me some code, okay? But inside the process, we know that we switch from the old code to the new code. But you are still that process, the orange process. Okay? Now, inside the kernel, it's very easy to understand. First of all, when you fire the call, okay, you type enter, and then you hit the execute system call execution, and you specify the file. The system call first thing is to look for that file. Okay? If the search is failed, it will return -1 and say that, yeah, I cannot switch. Okay? And you go away, okay? I give you return value -1. Okay? Then this is search. And if the search is successful, then something bad happened. What is the bad thing? Because we executed another program. So that means the original program, let's say the original program tell me that to allocate 1 giga memory, okay, 1 gigabyte memory. Actually, you don't need it in a new program. So the malloc will be clear. Global variable is totally depends on which code, right? One code has 3 globals, another code has 5 global variables. So they are not compatible. So before the switch, will clear the global. Local variable don't need it. I don't care which function you're executing, but when you go to the new code, you will always start from the main. So all the local will be clear. The code is about to change. Then next is very easy. It's the end. Okay, it's the end. It's so simple, right? You clear all the memory and then you switch. And this is the boring part, right? As I told you. Now we are going to something kind of exciting. So what is the meaning of kind of exciting? The wait and exit system call. Okay? The wait and exit system call actually works in a pair. What is the meaning of work in a pair? You know, the wait system call is wait for the termination of the child. Okay? So that means there is something inside the exit system call to tell another guy, that is the parent, that, oh, you don't need to wait anymore. So these two guys should work in a pair. Okay? This is quite hidden. In the previous illustration, I don't talk about it, okay? Because now we're going to the kernel side. We have to understand that, hey, how these two guys cooperate. And when you understand the cooperation, it's very interesting. Okay? So now we have actually 2 cases. Okay? The 2 cases is about the moment that you call the wait system call. Okay? Let's have a complicated scenario first. What is a complicated scenario? Is when a parent before this graph, okay, let's say we have called for, okay, these 2 guys already are separated and they have a relationship, parent-child relationship. Then this guy called waits and go to the kernel and do something, and the kernel say that, I know that you are waiting for a child termination, but your child is still living. Why don't you stay inside the kernel code and I don't release you? Okay, so you will be blocked. Okay, so we call it a blocking system call. We will be blocked there, and I put dots here. Now, how about the child? The child will continue the execution until something happens. Either you accidentally being terminated, let's say the segmentation box, or you voluntarily exit, like you call exit, or you call return 0 in the main function. So you will terminate. Okay, believe in me, when you call return 0 from the main function, eventually you are calling exit. Okay, so this is the same. And when the exit system call, actually exit is a system call, right? You will go into the kernel to do something, and then send a notification inside the kernel layer. So this is the big arrow. Send a notification to your parent. Now, how this mechanism can be done? Let's take a look. Okay, so this is the exit system call. Let's forget about the waits first. Exit system call start now. So what is the first phase of exit system call? First, we will look into the array of open files. Okay, array of open files. What should you do? You have to inspect every one of it and close them. So your lecturer before this class, okay, I don't know how many lecturers you have go through. They all tell you that you open a file, please close it. I say nonsense. Okay, because kernel will do it for you. Okay, it is a must. Okay, no matter what other files it is, it can be a database connection. It can be a normal file. Okay, it can be even more horrible stuff like a network connection or BT or whatever things. Once you know what's BT, right? Or donkey, okay, yeah, something like that. You terminate the program. Every open file, including network connection, will be closed because network connection is also keep inside this array. Okay, will be closed, and after this process is done, so that we know that all your own, you have ownership, right? You own that file, you own that socket, you own that network connection, own the database. All the ownership is terminated. Then it's time for you to terminate this process. Okay. I always say you, okay, who are you? You are the process, okay? Not you really own the file, but the process own the file. The process own that socket, own that database connection, okay? So the process queue them all. What's next? Next is deallocate all the memory, okay? So that's why another nonsense part, okay? People tell you that you remember to call malloc and then call free. I say maybe you don't need it. Why? When you call a system call, this will be terminated, or I say terminated, but deallocated automatically. Okay? So you will ask, hey, then why those lecturers telling us to do it? Okay? Why they tell you that F open and then you call F close? Why they tell you that when you do a malloc, you have to call free? Now let's go back here. Why you have to call F open and then F close? Okay? There is you can do a try, okay? But I think it's very horrible, okay? Maybe you go ahead by yourself. I don't do it here, okay? Because of this array, okay? This array is kind of fixed or hard code, okay? The limit here, we call it open file limit, okay? Yeah. So where's my limits? So there is a command for you to look up the limit. Can you find out the open file limit? I found it. Can you see it? Maybe you cannot. Okay? So you can type this command on your Mac or on your Linux. Okay? They both exist on Mac and Linux. I don't care about Windows. The Windows sucks. Okay? Yeah, really sucks. Okay? Last week, okay, I'm in LT6, okay, we are playing with a new Linux support called Docker, okay. Someone claimed that Windows can use Docker, and we find that Windows really sucks, okay. It don't support the keyword double quote. When you press double quote, it's stuck, okay. When you remove all double quote, it works. Yeah, that's Windows, powerful, okay. Yeah, no one expect that, okay. Open files. So the limit is 1024. So you can try by yourself. You try to write a program, indefinitely construct new file names, okay? Remember, you have to construct new file names, okay? They keep on open them without close for 1024 times, but actually it's not, because you already have 0 for standard in. Array index 0. Array index 1 for standard out. Array index 2 for standard error. So -3. So 1021. Then you cannot open anymore. Okay? And that's why some people tell you that, yeah, you have to open the file and close. It's because there is a limit. Okay? But, well, who cares? As long as your program only run for 1 second. Is it making any sense if your process only run for 1 second, and after that 1 second you terminate your process, you clean up this array? Okay, who cares about the limit? Okay, but another point is that how about you're writing server program? A server that will run for 24 hours every day, say 1 week, 7 days, 24 times 7. We expect you run for forever. Okay, you don't need to reboot your computer. Then you have to take care of it. Let's say your server process will open a file, but you forgot to close it. Then eventually, maybe after 2 days or 2 weeks, okay, then your boss will come to you and say, hey, why your process stuck there? Okay? It's the process stuck. Okay, the process don't allow you to continue to open, but it is still running. Yeah, you feel that the irony there. The irony there is you're still there, but you don't want to work. Okay, just like nowadays, okay, it's too cold, you don't want to work. Okay, it's the same thing. So this is the limit. Another limit is about this guy. Okay, why people tell you that after malloc you have to free? Okay, because this box, I write a box here, has a limit. Okay, the limit doesn't exist in 64-bit CPU because you never hit it. Okay, you can never hit it. Okay, I don't know how many 100 years. Okay, we will hit that limit. But using 32-bit CPU, this box is 4 gigabyte. Yeah, that means that in 32-bit CPU setting, you cannot run a process that allows you to malloc for more than 4 gigabyte. Okay, so this block is a bound there. So if you're using memory, but you want to be an environmental friend, you want to be cycle and keep on running for, let's say, for a decade, okay, please, after you malloc free, okay. So next step, after all the deallocation of files, memory, what are the things that you have to deallocate? Seems that all the things you allocate have been free except inside the kernel, the structure inside this double linked list, right? This pair of guys is double linked list, right? Now, what's this guy? Okay, I put a zombie icon here. Then you have to play what's this game? Plant versus Zombie. No one playing now? Okay. So this is zombie. So in computer, we also call it zombie process. So what is a zombie process? It's a process that we don't have any code to run. Can you imagine there's a process don't have any code to run? Yeah, this is this guy. Because we deallocate on memory, deallocate on the code, deallocate any file, so you don't have anything to run. And there is some way to construct a zombie process. Okay, we have a code in GitHub already. You can create zombie process. Okay, and what is zombie process? Zombie process is just this guy standing inside the double linked list, waiting for your termination. Okay, it's standing there waiting for termination, and who will do the termination is the wait system call. But the wait system call, before it knows that there is zombie exists, he has to be notified. Who called the wait system call? The parent. The parent will be notified by this zombie. Before it becomes a zombie, he will send a so-called signal. The name, this is the name, okay, called sick child. Or signal child signal, yeah, this is a matter. Okay, we call it sick child. So the sick child sent to this guy, and what happened to this guy? This guy, if this guy don't call wait system call, it will ignore the zombie. But when he has the wait system call ready, okay, so I'll skip this short summary, okay. When this guy has the wait system call ready, then everything's changed, okay. So what happened here? When this guy inside the wait system call and receive sick child, it will free from the kernel and we execute its original code. Now, what is going on here? Let's see. I don't have enough time, huh? Okay. So next time we will continue to talk about it. Okay, talk about the wait system call handling, and after that, on tomorrow, okay, we will demonstrate how damaging the zombie process is. Okay, a zombie process is very damaging. Okay, and I will introduce to you a program. This program, we call this program an infinite zombie factory. Okay, it's a program that can generate infinite number of zombies so that you render your computer in a useless computer. Okay, yeah, useless in the sense that you will still see the computer working, but it cannot produce anything useful. Okay, you're welcome to execute it on your computer. Okay, the worst case is you have to reboot. Okay, but don't run in any proper computer. I will bring my PC for crash to come to show you all the circumstances. Okay, so let's stop here.